Here's a calculus test on the optimization and curve sketching unit. Question number 1 says, given the graph of f prime of x, state the intervals of increase and decrease for f at x, then sketch a possible graph of f at x. So it's important to notice that the graph we're given is the graph of f prime of x, and we're interested in the intervals of increase and decrease for f at x. Well, I know f at x would be decreasing if f prime of x is negative. So I'll make a note of that here. It'll be decreasing if f prime of x is less than 0. And f at x would be increasing if f prime of x was greater than 0. So now that I know what I'm looking for, let's go to the graph and let's find when is the derivative negative, when is it positive. The derivative is negative when x is less than -4 and also when x is bigger than 2. So those would be the intervals where f at x is decreasing. When is f at x increasing? Well, f at x is increasing when the derivative is positive, and the derivative is positive between x values of -4 and 2. Now I have to sketch a possible graph of f at x that has those intervals of increase and decrease. I need to be decreasing before -4. So before -4, I need to be decreasing. And then when x is bigger than -4, it switches to increasing. So that means at -4, there's a local min. I don't know the y value of the local min, but I'll put a point right here. I know that it's decreasing before that point and increasing after that point. And it's going to keep increasing until I get to an x value of 2. And then after 2, it switches to decreasing. So at 2, there's a local max somewhere. I'll put it up here. I need to increase up to that point. And then after that point, the function starts decreasing. So there's a possible sketch of an f at x function that has the correct intervals of increase and decrease. Question number 2. Find all points of inflection and state the intervals of concavity for this function here. Well, I know at a point of inflection, the second derivative is going to be 0 or undefined. So let me find the second derivative. I'll have to first find the first derivative, f prime of x. If I just use the power rule for each term, I get 4x cubed minus 9x squared plus 1. The second derivative, just differentiate the first derivative, I get 12x squared minus 18x. That's a quadratic, it can't be undefined, but it could be 0, so let me set it to 0 and solve. I'll common factor out a 6x from both terms, and I get 2x minus 3. So I'll have two x values here. I get an x value of 0, and also an x value of 3 over 2, which I could just write as 1.5. At those two x values, there might be a point of inflection. I'll have to do a test to see if the function changes concavity around those points or not. So let me do a point of inflection test. In my point of inflection test, on the left, I'll use negative infinity. On the right, I'll use positive infinity. And in between, I'll use 0 and 1.5. Those two dividing points create my 3 intervals where I can check for the concavity of the function within each interval. I'll do that by plugging a test value into the second derivative. And then that will tell me, based on its sign, whether the original function is concave up or concave down within each interval. So let's pick some test values. Between negative infinity and 0, I'll pick -1. Between 0 and 1.5, I'll pick 1. And from 1.5 to infinity, I'll pick 2. I need to sub each of those values into the second derivative, which I have its factored form here. I'll sub into that factored form. If I sub -1 into the second derivative, I will end up getting a positive answer. That tells me that the original function is concave up in that interval. If I sub 1 into my second derivative, I get a negative answer, which means the original function is concave down in that interval. And if I sub in 2 to the second derivative, I get a positive answer, so once again, it is concave up. So notice there was a change in concavity at 0 and at 1.5. So that means there are 2 points of inflection. There's a point of inflection at 0, and I'll calculate the y value from my function. The y value will be -1. And at 1.5, and I can calculate the y value by subbing into the original function for x, sub in 1.5. I get about -4.6. So at those 2 points, there are points of inflection. There are changes in concavity at those 2 points. I can also state the intervals of concavity based on my chart. I know that the function is concave up in the interval between negative infinity and 0, and also from 1.5 to infinity. And it's concave down in the interval between 0 and 1.5. Question 3. Given the graph of f double prime of x, state the intervals of concavity for f at x. Well, I know the sign of the second derivative tells me the concavity of the original function. I know the original function would be concave up if the second derivative was positive, if it was greater than 0. And the original function would be concave down if the second derivative was negative. So let me look at the graph of the second derivative and see when is it positive, when is it negative. Let's start with when is it positive. The second derivative is positive when x is less than -3 and also between 0 and 3. So I know those are the intervals where the original function would be concave up. And when is f of x concave down? It's concave down when the second derivative is negative. It's negative between -3 and 0, and also when x is bigger than 3. So I'll write those intervals. Let's move on to question 4. Determine the absolute extreme values of f of x on the interval between -5 and 3. The key thing here is that we are finding the absolute extreme values. I know the absolute extreme is going to happen either at one of the endpoints of the interval or at one of the critical numbers between those endpoints. So let's find the critical numbers of f of x. The critical numbers are numbers that make the first derivative be 0 or undefined. So let's find the first derivative. Using the power rule, I get 3x squared minus 12. If I set this to 0 and solve, common factor of 3, x squared minus 4. That's a difference of squares. It factors to x minus 2, x plus 2. So I have two critical numbers. I have x equals 2 and x equals -2. Those are my critical numbers. If I want to find the absolute extrema on the interval between -5 and 3, I'll have to test the value of the function at the endpoints of the interval, so at -5 and at 3, but also at any critical numbers between -5 and 3, and we found two of them. We found -2 and 2. So I'll find the value of the function at all four of those x values. Whatever the highest one is, that's the absolute max, and whatever the lowest one is, that's the absolute min. If I sub in -5, I get -63. If I sub in -2, I get 18. If I sub in 2, I get -14. And if I sub in 3, I get -7. Now from these y values, I need to find the smallest one and the biggest one. Well, the smallest one is -63, and the biggest one is 18. So I have my absolute min and max points. The absolute min is the point -5, -63, and the absolute max is the point -2, 18. Question 5 says sketch a graph of a possible function f of x that meets the following set of conditions. F prime at -4 and f prime at 2 are 0. That means the original function has a slope of 0 at those 2 points. F prime of x is less than 0 when x is bigger than 2. When f prime of x is less than 0, that means f of x is decreasing. So it's decreasing when x is bigger than 2. F prime of x is bigger than 0, so f of x is increasing when x is less than -4 and between -4 and 2. So I've got the intervals of increase and decrease. I notice it also tells me about the second derivative. The second derivative is less than 0, meaning the original function is concave down when x is less than -4 and bigger than -1. And lastly, the second derivative is positive, meaning f of x is concave up between -4 and -1. Before I try and graph this, let me organize this information onto a number line. I can see from the information given that I will use -4, -1, and 2 as the dividing points on this number line, because that's where the signs of the first and second derivative seem to be changing. I'll record the sign of the first derivative above the number line and second derivative below the number line. I can clearly see that the original function goes from increasing to decreasing at x equals 2, so there's a local max at x equals 2. And there's a change in sign in concavity at -4, and also at -1. So there's points of inflection at those two x values. Also, I can't forget that I want a slope of 0 at -4 and 2. Well, at x equals 2, there is a local max. So of course, there's going to be a slope of 0 there. But there is no local max or min at x equals -4, but I still need a slope of 0. So I'll be making this shape at x equals -4. For each of these 4 intervals I've created, let me draw the correct shape in each interval. When x is less than -4, the function needs to be increasing and concave down. Between -4 and -1, the function needs to be increasing and concave up. Between -1 and 2, it needs to keep increasing but change to concave down. And then lastly, when x is bigger than 2, it needs to be decreasing and concave down. Notice I have my point of inflection at x equals -4, another point of inflection at x equals -1, and a local max at x equals 2. just like I said we were supposed to have over here. Also notice I have the slope of 0 at -4 and at 2. So there's that graph done. Let's move on to the next question. Question 6 says state the equation of any asymptotes for the following functions. So I'm going to check, are there any horizontal or vertical asymptotes for this function? Since the denominator is degree 2 and the numerator is degree 1, whenever the denominator is a higher degree, the horizontal asymptote is going to be at y = 0. The vertical asymptote is going to be at whatever x value makes this function undefined. It would be undefined if the denominator was 0. Let me just rewrite that denominator in factored form. Right, I could write it as x minus 10, x plus 2. So you could see that x values of both 10 and -2 would make the denominator 0, which means there are vertical asymptotes at both x equals -2 and at x equals 10. For part B, why don't I factor that denominator while I'm at it? I could common factor a -2x from both terms. And now I'm going to write the equations of the horizontal and vertical asymptotes. Horizontal asymptote, I'll actually look at the original version of the function. Notice that the numerator and denominator are both degree 2. When the numerator and denominator are the same degree, to get the equation of the horizontal asymptote, it's at y equals, you just find the quotient of the leading coefficients. 4 divided by -2 is -2. Vertical asymptote, whatever x value makes the denominator be 0. An x value of 0 and an x value of 2 both make the denominator 0, so there are vertical asymptotes at both of those places. Question 7 says, using the graph provided, list all letters that apply to each question. And notice this graph that's being provided is the graph of f at x. Part A says, where is f prime of x equal to 0? That means where does f at x have a slope of 0? So where could I draw a horizontal tangent line? Notice I could draw a horizontal tangent at B, at D, and at H. Part B says, where is f double prime of x equal to 0? So where is this function neither concave up or concave down? I like to look for the points of inflection. So at C and F, it looks like those are places where the function is changing concavity. So the second derivative must be 0 there. Where is f prime of x greater than 0? That means where is f at x increasing? It's increasing at C and at I. Those are the two places where the tangent line drawn there would be going up to the right. Where is f double prime of x less than 0? That means where is f at x concave down? It's concave down at D and at E. Part E says, when is the first derivative negative and the second derivative negative? That means we're looking for a part of the function that is decreasing and concave down. Decreasing and concave down, the only point that meets that criteria would be point E. Number 8, for the function f at x, determine the critical points and classify them using the second derivative test. Critical points are points that make the derivative 0 or undefined, so let me find the first derivative. I'll use the power rule on each term, and that would give me x squared minus 3x plus 2. That's a quadratic. It can't be undefined, but it could be 0. Let me factor it. It would factor to x minus 2, x minus 1. So it would be 0 if x was either 1 or 2. Those are my critical numbers. My critical points, if I sub 1 and 2 into the original function, I get 1.83 and 1.67 as my corresponding y values. I need to check, are those points local max points, local min points, or neither? And it says to use the second derivative test. The second derivative test, I just sub each of those critical numbers, 1 and 2, into the second derivative to see if the function is concave up or down at those points. So let me find the second derivative. If I differentiate the first derivative, I get 2x minus 3. F double prime at 1, if I sub in 1 into that second derivative, I get negative 1. The fact that it's negative means that at an x value of 1, f at x is concave down. Therefore, it is a local max at the point 1, 1.83. Let's evaluate the second derivative at the second critical number, at 2. If I sub in 2, the second derivative has a value of 1. Since that's positive, that means the original function when x is 2 is concave up. If it's concave up, it means we have a min point at an x value of 2. Therefore, local min at 2, 1.67. Question 9 says, use the algorithm for curve sketching to sketch a graph of f at x. It's a polynomial function, so I know there are no restrictions on this function. There are no asymptotes or holes. So for part 1, I'll write none. I need to find the x and y intercepts of this function. Notice the x-intercepts are given. I just need to solve for the y-intercept, and I can calculate that just by subbing in 0 for x, and I would get -9. So 0, -9 is my y-intercept. And now let me determine the critical points by finding what makes the first derivative 0. So I'll find the first derivative. That would give me 12x cubed minus 24x squared minus 12x plus 24. If I set this to 0 and try and solve, I notice factoring by grouping would work. I could take a common factor from the first two terms and a common factor from the last two terms, and I'm going to end up with a common binomial. From the first group, I'll take out a 12x squared, and that leaves me with x minus 2. And from the second group, I'll take out a -12, and that leaves me with x minus 2. I have the common binomial of x minus 2. When I remove that as a common factor, I'm left with 12x squared minus 12. I notice that 12x squared minus 12, I could remove a common factor of 12. I suppose I could have done that at the start of this question before I did factoring by grouping, but it works at this point as well. And now that x squared minus 1 is a difference of squares, I can factor that to x minus 1 times x plus 1. So I have 3 critical numbers. X equals -1, 1, and 2 are the critical numbers. I can sub all of those into the original function, get the y values, and then those are my critical points. So my corresponding y values would be -28, 4, and -1. Let's move on to part 4 that says determine the possible points of inflection. I know possible points of inflection are going to happen when the second derivative is 0 or undefined. So let me find the second derivative. The second derivative, when I differentiate my first derivative, I would get 36x squared minus 48x minus 12. Let me set that to 0 and try and solve it. Let me common factor out a 12 first. And then if I try and factor this quadratic further, it doesn't factor, but I could find its zeros by using quadratic formula. So x would equal 4 plus or minus the square root of -4 squared minus 4 times 3 times -1 all over 2 times 3. Underneath the square root, simplifies to 16 plus 12, that's 28. So it goes to root 28, which I could simplify to 2 root 7. Now let me actually get the approximate value of these two zeros. I get 1.55 and -0.22. Let me sub those values into the original function to figure out where the possible points of inflection are. When I sub those in, I get y values of -14.36 and 1.32 respectively. Step 5, 6, and 7, I need to make a chart that uses my critical numbers, points of inflection, and vertical asymptotes to analyze the intervals of increase, decrease, and concavity, and then I'll make sure to identify the local extrema and points of inflection. So I have 3 critical numbers and 2 possible points of inflection. So I will use those 5 numbers as my dividing points to create my intervals. Okay, there's my chart where I've used my critical numbers and my possible points of inflection as dividing points. I'll pick some test values within each interval. So I'll choose -2, -0.5, 0, 1.5, 1.7, and 3 as my test values. I'll sub each of those test values into both the first and second derivative and record the sign of the answer. Now that I've filled all those out, let me comment on what f at x is doing in each interval. In the first interval, f at x is decreasing and concave up. Second interval, it is increasing and concave up, then increasing and concave down, decreasing and concave down, decreasing and concave up, and then finally increasing and concave up. So from that chart, I can see all my intervals of increasing and decreasing and the intervals of concavity. When I draw my graph, I'll make sure I clearly label any local extrema and points of inflection. So I'm just going to draw each of these shapes in the corresponding interval, and then I have my graph. I should also make sure that I graph all of these points that I've found that are on my function. Let me do that quickly. All right, let me try and sketch the function with the correct intervals of increase, decrease, and concavity. All right, should have been decreasing when x is less than -1 and between 1 and 2. So when x is less than -1 and between 1 and 2, it was decreasing. And it should have been increasing between -1 and 1 and when x is bigger than 2. So increasing between -1 and 1 and when x is bigger than 2. Good. Concave up in those two intervals. So concave up there and also concave up here. And then concave down just between those two values of -0.22 and 1.55, which is this section right here. Okay, let's finish the test off with an optimization question. It says to pick 10 or 11, not both. I'll show you the solution to 10. Feel free to leave an answer in the comments about what the solution to 11 is. Number 10, a closed box with a square base is to be made to have a volume of 10,125 centimeters cubed. Let me just start by drawing a box with a square base. Since this box is a square base, I'll label the length and width of the base as x, and the height, I'm not sure, I'll use h for the height. I know the volume of this is fixed, so I know my constraint, the volume, is 10,125 centimeters cubed. And I know volume of a square base prism is area of base times height, so that would equal x squared times h is equal to that 10,125. I'll continue working with that in a minute. It continues to say the material for the top and the bottom of the box costs 3 times as much as the material used for the sides of the box. Determine the dimensions that will minimize the cost of the box. So the cost is based on the material used to make the box, so it's based on its surface area. So let me make an equation that I'm interested in minimizing. Let me start by making a surface area equation for this shape. Surface area of this shape would equal, the top and the bottom are both x squared, so it would be 2x squared, plus all the sides of this box, the front, back, left, and right, are all x by h, so 4xh would find me the area of all those sides added together. Now it tells me the cost of the top and bottom is 3 times as much as the sides of the box. So if I generate a cost function, I don't actually know what the cost is, but I know the top and the bottom are 3 times as much as the sides. So if I assign the sides a cost of 1, the cost of the top and bottom would be 3. So 3 times the area of the top and bottom plus the area of the sides would give me an idea of how much it would cost to make this box. Now what I have to do is I need to make this cost function work for my box that has to have a volume of 10,125. So what I need to do is use this relationship to isolate either x or h. I'll isolate h. So if h equals 10,125 divided by x squared, I now know that to keep the volume at 10,125, the height has to be equal to 10,125 divided by x squared. So I can replace the height with that. So now I just have cost in terms of x, and that's 6x squared plus 4 times x times h. I'll simplify this function. This x will cancel with one of those, and 4 times 10,125 is 40,500. And this is x to the power of -1. If I bring that power of x up to the numerator, it makes the exponent negative. I'm interested in the minimum value of this function. I know at a minimum value, the derivative is going to be 0. So let's find the derivative, which is just 12x minus 40,500 times x to the -2. I'll set this to 0, and then I'll solve this equation. I'll move this term to the other side. Let me multiply both sides by x squared, divide both sides by 12, raise both sides to the power of a third, and I get x equals 15. Now, I should verify that minimizes the cost by doing a first or second derivative test. Let me just quickly do a first derivative test. Okay, so I'm going to pick a test value between 0 and 15 and between 15 and infinity. I chose test values of 1 and 20. I'll sub those into my first derivative to see if it makes it positive or negative. If I sub in 1, it makes it negative. If I sub in 20, it makes it positive. That means the cost function was decreasing before 15 and then increasing after 15. So that means at 15, we have a min. And also, when x is 15, we could solve for h. If I sub in 15 into my height equation for x, I figure out the height is 45. A 15 centimeter by 15 centimeter by 45 centimeter box will minimize the cost.
Jensen math.